Hello everyone, welcome to the 16th tutorial class on digital communication. In this class, we shall discuss about the minimum shift key digital modulation technique. So this is the basically last topic of the digital modulation technique. And in this class, we shall discuss about the waveform and the properties of MSK, and we shall also observe uh, bandwidth and the signal space diagram of MSK, and followed by the generation and detection technique of MSK. Okay, so MSK, that means the full form of MSK is minimum shift keying, and it has been widely used in satellite communication where spectrally efficient modulation technique is required. Now, before going to the details of the MSK, let's revise the concept of QPSK and OQPSK. The concept of QPSK is already discussed in the previous class, but for better understanding, we shall again discuss about the QPSK and OQPSK. Now, okay, so let's start. Uh, we already know that cos 2 pi FCT and sin 2 pi FCT, where FC is the carrier frequency, are known as the orthogonal signal. That means these two signals can be used for detection purpose without any problem, and these two signals are known as the quadrature signals. Okay, so two carrier signals which are quadrature in nature. That means their phase difference is pi by 2. Okay, now let's consider a binary stream AK, where AK can take plus minus 1 if we consider polar energized line coding. So value of AK can take either plus 1 for 1 and minus 1 for 0. Okay, where K can take 0, 1, 2, etc. depending on the number of bits. And the bit rate is 1 by T. That means bit duration is T second. Okay, now we can separate this input binary stream into two different stream known as the in phase stream and quadrature stream, which is nothing but even bits and odd bits. Okay, and the example will be discussed in the next slide. Now the two pulse train modulate the in phase and quadrature component of the carrier, and ultimately we get the summation st, and this is nothing but the QPSK signal, and that can be represented by this following equation. So st is 1 by root 2 AIT into cos 2 pi FCT plus pi by 4 plus 1 by root 2 AQT into sin 2 pi FCT plus pi by 4. So this is basically conventional formula. You can also neglect pi by 4 term if you want to use conventional QPSK. Okay, so you can see that in phase uh, bit stream is multiplied by cos 2 pi FCT, and quadrature bit stream, that means odd odd bit stream, are multiplied by sin 2 pi FCT. Okay, so this two term is nothing but two separate binary BPSK signal. Okay, so you can see that AI can take either plus minus 1, it can also take either plus minus 1. So plus minus 1 is nothing but phase difference of 0 or pi, pi. So for plus, the phase difference is 0, and for minus, phase difference is pi. So this is also represent a BPSK, and this also represent another BPSK, but they can easily detect it and independently, as they are orthogonal in nature. That means cos 2 pi FCT plus pi by 4 and sin 2 pi FCT pi by 4 are orthogonal in nature. Now coming to the next slide. We get the conventional QPSK formula is like this. Now using trigonometric identity, this formula can be rewritten as like this: st equal to cos 2 pi FCT plus theta t. Okay, now theta t can be taken, can take either value of 0, plus minus 90 and 180, depending on the different four combination of AIT and AQT. Okay, so as AIT and AQT can take both +1 and -1 value. So obviously, depending on this different combination, it can take either 0 0 0 plus minus 90 and 180. So for 0 0 it can take 0, for the 0 sorry, +1 -1 it can take plus 90, like this. Okay. So here you can see that a QPSK transmitter. This is the input bit stream, where you can see that input bit stream is initially A0, A1, A2, A3, A4, A4, A5, A6, A7. Total 8 number bit is there, and the bit duration is from t second. That means A0 is lasting from 0 to t second, and A1 is from t to 2 t second. Okay. So you can see that A0, A1 are and A5, A6 are plus, and A2, A3, A4 these are -1. That means these are the 0. Okay. So these are the input stream. Now we have to demultiplex it into the odd and even bit. Okay. So you can see that this one is the even stream, this one is the odd bit. That means this one is the in phase, this one is the quadrature bit. So you can see that now first bit is, if you consider the even, so A0, next one is the A2, next one A4, A6. Okay. So but in case of demultiplexing, the symbol duration will be from 2 tt second. Okay. So so for next 2 tt second, A0 will be remain +1, and from 2t to 4t, A2 will be -1. Similarly, from 4t second to 6t second, A4 will remain at -1, and from 60 to 80, A6 will remain +1. So you can see that symbol duration is 2t. Okay. Similarly, AQT, and it has been started from A1. So A1 is 1. So but it remain here for the demultiplex or quadrature bit stream. It will last up to 2t second. Okay. So this one is the AIT, and this one is the AQT. Now if we multiply it by cos 2 pi fct plus pi by 4, and if we multiply AQT by sin 2 pi fct plus pi by 4, and ultimately if we add them, we get ultimately QPSK signal. Now coming to the another part, another version of the QPSK, which is known as the offset QPSK or OQPSK. And the difference between two process QPSK and OQPSK is very minor. Sorry. uh, the difference is basically depending on the alignment of the two bit stream in phase and quadrature. If we see the previous case of QPSK, here both AIT and AQT has been started from 0 second. Okay. But here in case of OQPSK, there is offset or shift between in phase and quadrature bit stream by t second. Okay. Here you can see that AIT has been initially started from -t to t second. Okay. Where QT has been started from 0 to 2t second. Okay. The concept between this is that A0 initial bit is A0, and after that A1 has been started. So obviously A1 has been started after t second. So if we consider as offset, and if we introduce in the corresponding in phase and quadrature bit stream, that means that there is delay between them. So that is the main difference for the OQPSK bit stream. Now due to this bit stream, there has been severe impact on the corresponding phase difference. Okay. Now let's see that. So if you see that the difference between QPSK and OQPSK will be clearly understood. Okay. So again, I am telling you that there is a phase shift of t second between AIT and AQT. AIT initially has been considered that start from -t second, whereas AQT has been started from t second. Sorry, 0 second. Okay. Now, now the difference in QPSK and OQPSK depending on the phase change. Okay. Now, as the QPSK, if we consider QPSK, due to the coincident alignment of AIT and AQT, the carrier phase can change only once every 2t second. So consider this one is the AIT and this one is the AQT. AIT means A0, A2, A4, A4, 6, and A1, A3, A5, and A7, which are the odd bit. These are the basically quadrature bit stream. So as both of them are started from 0 second, so obviously they are coincident align. There is coincident alignment. So carrier phase of the carrier can change only after 2t second, because in case of in phase or quadrature phase bit stream, the duration of the symbol is 2t second. Okay, so after 2t second, at this point the corresponding phase shift can take. And obviously after 2 to second, that means at 40 second, next phase shift will change, will occur. And after similarly at 60 second or 80 second, corresponding phase shift will occur. Now there is the conventional rule depending on the um, pattern or the combination of AIT and AQT. um, Four phase can uh, oh, sorry, four phase uh, can be taken. Okay. So here if we so let's consider the example. Here a0 equal to 1 and a1 equal to 1. Okay, but next a2 equal to -1, a3 equal to -1. So in this scenario you can say that 2 bit has been changed. Okay, so if 2 bit has 2 bit change its sign, so obviously the phase shift will be 180. But if one bit is changed, so obviously phase shift will be plus minus 90. So after you can see that here uh, the phase shift is 180 for a0 a1. The corresponding phase shift is 0, but at this point corresponding phase shift is 180. A4 a5, if we consider a4 a5, a2 is -1, a4 is -1, but a3 is -1, but a5 is +1. So obviously one bit has been changed, so plus 90 phase shift has been introduced here, like this. Okay, so this one is the for a typical waveform of the QPSK. The main problem of this type of waveform for the QPSK is the abrupt or sudden change of phase shift of 180. Whenever there is phase shift of 180, uh, there is abrupt change of phase. That means uh, if we consider the envelope of a QPSK, so in that case envelope will not constant and it will cross the 0. Okay, so envelope will go to the 0, and this phenomenon will lead to unnecessary frequency side lobe in the spectrum. Okay, now this spectrum will leads now this unnecessary out of band radiation on the satellite link, and it also create interference with the others communication system. So our main objective should be to get the constant envelope or to minimize the abrupt phase change, like 180 phase shift. So to minimize so that the side lobe in the spectrum can be reduced. So considering these facts, OQPSK slightly overcome those problems. So here you can see that there is slightly different alignment. So both binary component cannot change simultaneously. Okay, one component has transition in the middle of the other symbol. Hence, only one component can switch at a time. So here you can see that a1 can last from 0 to 2t second. However, a0 can last from -2 t second. So obviously at t second there will be phase shift, but as a1 is last up to 2t seconds, so obviously there is no change at this point. So obviously at this region only one bit can change. Similarly at this scenario, if we consider 2t second, a2 will AT is constant wherever A1, sorry, yeah, A2 from T to 3T time duration, A2 remain constant. However, A1 has been changed, or odd bit has been changed. So obviously there will be phase shift. So, but the main fact that I want to mention that it eliminates the possibility of 180 phase change, 180-degree phase change, and phase change can limited only 0 to plus minus 90 degree at every t second. So here you can see that there is phase shift of 90 degree. Okay. Similarly here this is on minus 90 like this. So when a QPSK signal undergoes a band limiting, the resulting intersymbol interference cause the envelope to drop slightly in the region plus minus 90-degree radiation phase transition. So here you can see that the discontinuity in the envelope has been reduced due to the removing of abrupt phase change. Okay, so envelope does not go to zero as it does not in the band limited QPSK case. This effect reduce or rapid phase shift reduce the out of band interference. Okay, now these two phenomenon has been further improved in case of MSK. So if you focus on this fact that we want to minimize the phase discontinuity, or you want to get the constant envelope, so MSK basically deals with them. Okay. So how can we get a constant envelope with continuous phase? That can be achievable by MSK. So MSK can be thought as a special case of OQPSK, with where we use sinusoidal pulse weighting. So what is sinusoidal pulse weighting? That can be explained later. So here sinusoidal pulse are used instead of rectangular shape. Okay, again I'm telling you that, sorry, here sinusoidal pulse are used in case of rectangular shape symbol or bit, and the corresponding modified signal can be defined as the MSK, and it can be written as AIT cos pi t by 2t into cos 2 pi fct plus AQT into sin pi t by 2t into sin 2 pi fct. Okay, now cos pi 2 by 2t and sin pi 2 by 2t, these are used to produce sinusoidal like symbol. Okay, and they are produced, that means their time period has been selected such a way that cos pi 2 pass through 0 at the end of the symbol time AIT, and sin pi by 2 pass through 0 at the end of the symbol AQT. Okay. Okay, sorry for the interrupt. So you can see that cos pi t by 2t and sin pi t by 2t are used to create sinusoidal pulse. Okay, instead of rectangular shape. Okay, so here you can see that this one is the sin pi t by 2t. It has been start from 0 second, and its time period is 4t second. But the duration of AIT or sorry, the duration of AQT is 2t. You can see that. Yeah, you can see that for AQT, for each symbol A1, the duration is 2t. So here it was mentioned that uh, sin pi t by 2t is is passing through 0 at the end of the symbol, each symbol in AQT. So here 2t, 4t, 6t. So you can all case you can see that these are passing through 0. Whereas in case of cos 2 pi t by 4t or cos pi t by 2t, mm, pass through 0 at the end of the symbol time in case of AIT. So it's from this one is the TT, sorry, this one is the 2T, this one is the 3T, sorry, uh, sorry, this one is the T, 3T, 5T. Okay, so at the interval of 2T second, sine pi t by 2T becomes 0. Okay, so using this property, we can convert a rectangular shape pulse into the sinusoidal pulse. So just if we multiply AIT with the cos pi t by 2T, it will become sinusoidal shape. And similarly, if we multiply AQT with sin pi by 2T, it will become sinusoidal shape, as AIT can take only +1 -1 value. So if we multiply 1 with the sinusoidal signal, it will become similarly sinusoidal value. But there will be a phase shift depending on the polarity or sign of the corresponding in phase bit stream or carrier quadrature bit stream. Okay, now coming to the next slide. So here you can see that uh, this one is the AIT. So AIT has been started from -2 and start and it has been continue up to t second. Okay, so if we multiply this rectangular shape, that means its value is +1, so it is, if we multiply by cos pi by 2, so the shape will remain same. Okay, so in the next time duration, uh, so cos pi t by 2T, it will be continued like this. So that means in the next time duration, that means from t to 3T second, the value of cos pi t by 2T is negative. But here the value of A2 is also negative, -1. So -1 and -1, that means positive. That means there is a phase shift in case of A2. That's why it will again become positive. Okay. Now next A4. A4 is again -1. So whenever there is -1, there will be, sorry. Now my next bit is -1. So there is no phase change. That means this signal will be continued. As the next symbol is +1, obviously there will be again phase shift. That means so here you can see that cos in this first case, cos is positive, negative, positive. Here cos is positive, but the symbol is negative. So positive and negative, negative. In this case, you can see that. So you can again positive, negative, positive, negative. So during A6 symbol, cos pi 2 by 2T is negative, but the symbol is positive. So if you multiply positive with negative, it will become negative. So obviously the sign shape of the symbol is negative. Okay. So this will, you can see that instead of rectangular shape, it will become a sinusoidal shape. Okay, so just multiplying with the corresponding cos pi t by 2T. So here the time duration or bit duration is very important. That should be, time period should be 40 for the cos pi t by 2T. Now if we multiply it cos 2 pi fct, it will become like this. Okay, it will become like this. Now similarly, sinusoidal shaped odd bit stream, that is AQT into sin pi t by 2T, and the quadrature carrier AQT into sin pi t by 2T into sin 2 pi fct are shown below using the same formula. Here you can see from 0 to 2T, sine is positive, so and the bit is positive, so obviously you get positive pulse. Next, sine is negative, but also sine, bit is also also positive, also negative, so negative negative positive, that means we get again sinusoidal as positive. And next, sine is positive, fi is also positive, we get the positive sinusoidal. But in the next case, sine become negative, but the a7 become positive, so positive negative, that means negative, so we get the corresponding negative pulse. And if we multiply it with the sin 2 pi fct, we get the this type of signal. Okay, so the main thing that we want to mention that AIT cos 2 pi or cos pi t by 2t or AQT sin pi 2 by 2t are basically smooth signal. Okay, and these are multiplied with the in phase and quadrature carrier, that is cos 2 pi fct and sin 2 pi fct. Okay, so so here you can see that phase does not change or signal do not change abruptly like QPSK. So as the signal does not change abruptly in case of QPSK, sorry, like the QPSK, so MSK can be called as a special case of OQPSK or shaped OQPSK, where we use shaped rectangular pulse or sinusoidal weighted pulse for the generation of the uh, um, generation of the quadrature carrier. And for this fact, low side lobe can be generated, and that leads to the minimization of the interchannel interference. Now coming to the next, that is the MSK composite MSK signal. So we get the two carrier AQT sin pi 2 by tt into sin 2 by fct and AIT cos pi t by 2t into cos 2 pi fct. If we add them, we get ultimately uh, MSK signal. Okay, so okay, now this equation, that means addition of AIT cos pi 2 by 2t into cos 2 pi fct plus AQT sin pi 2 by 2t into sin 2 pi fct can be easily rewritten using the trigonometric identity like this, where we can write st cos 2 pi fct plus bkt into pi t by 2t plus phi k. Okay, and if we take common 2 pi t, so it will become cos 2 pi into fc plus bkt by 1 by 4t into t plus phi k. Okay, so where bk is the symbol which value become plus 1 if AIT and AQT have the opposite sign, and BQ uh, take become, or sorry, BQT is minus 1 when AIT and AQT have the same sign. That means we can write BKT is nothing but minus AIT multiplied with the AQT. Moreover, to maintain the formula, phi k has been introduced. So phi k is 0 or pi corresponding to the value of AIT that can take 1 or minus 1 respectively. Okay, so for 1, phi k value will be 0, and for minus 1, value of the phi k will be pi, so that the formula of ST can be maintained. And the corresponding waveform for the MSK, it will look like this. Okay, now this will be explained in the next slide. So how this, you can see that here there is no phase discontinuity, but you can see that there is a certain amount of frequency deviation. That means in some area high frequency, in some area low frequency. Like you can see that for 3t to 4t the frequency is low, but here in this case frequency is high. Okay, so how this happens, this can be explained in the next slide. And this one is a theta t, that is nothing but pi 2 by 2t into bk. So how this graph can be obtained or achieved, this will also be explained in the next slide. Now considering the above graph or figure, we can reduce, or you can deduce the following properties. So first of all, it has constant envelope. That means there is no discontinuity in the envelope. That means no sudden change in the phase, so that constant, so that envelope do not cross the 0, and we get the phase discontinuity in the RF carrier. And here you can see that Uh, if we uh, if we consider this part, that means consider phi k is 0. But in that scenario, you can see that value of bkt can take either +1 and -1. So, so this equation is similar to the FSK signal, where it can take either high frequency. So when bk is 1, the frequency is high. That means a plus. So a plus is nothing but fc plus 1 by 40. And there is also low frequency when bk is -1. So in that is denoted by f minus. So fc by 1 by 40, uh, the value of m minus. So the signal is an FSK signal with signaling frequency, high frequency and low frequency, f plus and f minus. And the corresponding frequency deviation equals to the half of the bit rate. That means delta f equal to f plus minus f minus, which is nothing but 1 by 2t. So this is the minimum frequency spacing or deviation which allow the two BFSK signal to be coherently orthogonal in the sense discussed in the section BFSK and BPSK. So hence the name minimum shifting has been used. Okay, so minimum shift of 1 by 2t is required to create MSK signal. Okay, moreover, MSK is also referred as fast FSK. Okay, next. Next, we have seen that there is a phase term which is given by bkt into pi t by 2t, that is called as the excess phase. So we define theta t as excess phase, like vkt into pi t by 2t, that is nothing but plus minus pi t by 2t. Okay, so you can see that, so depending on the value of bkt, theta t can be either increased or decreased. So theta t increase linearly during each bit, sorry, increase or decrease. Okay, sorry again. Sorry for the repeated interrupt for this particular class. We are there of excess phase for the MSK that can that is given by theta t bkt into pi t by 2t. Okay, now depending on the value of bkt, theta t can be increased linearly or decreased linearly. Consider bkt is the plus 1 for a particular time duration of t. So in that scenario, there will be an increase in the carrier phase by plus 90 degree. So you can see, so consider the first time duration from 0 second to t second. In that case, a0 equal to 1 and a1 equal to 1. So obviously bq bkt will be minus a it into aqt, that is 1 into 1 minus 1, sorry, minus into 1 into 1, that is minus 1. So for this case there will be minus 90 phase shift. So you can see that for first time duration the phase shift is minus 90 degree. Okay, so for the similarly, whenever there is bk equal to plus 1, in that case there will be plus 90 increase of carrier phase of plus 90 degree, and this increase of carrier phase plus 90 degree is corresponding to a BFSK signal at higher frequency. That means when phase will be increase, so in that case obviously frequency will also increase. So when the bk, that means bk is negative or minus 1, so there will be linearly decrease in the phase of 90 degree, and that is corresponding to a lower frequency f minus. So when, so you can see that this graph. So coming to the first time duration, bk is negative or minus 1, So in that case, the value of corresponding frequency is f minus. That means decrease in the low frequency, decrease in the frequency. So corresponding phase is also reduced. In second case, f plus. That means increase by plus 90 degree. Okay. So obviously phase is again minus 90 plus 90. That means it reached at 0 at 2t second. Okay. Again minus 1. So again minus 90 minus 1 minus 90 plus 1 plus 90, like this. So it should be keep in mind that whenever bk is minus 1, the frequency is reduced. When the bk is plus 1, frequency is increased. So again, if you see that, so at this point coming to this minus 1, so here you can see that there is reduction in the frequency, but when there is 1, so in that case the frequency is higher, that is a plus. So here again, in this case f minus a minus, but here in 4 to 40 to 5t, this is 1. That means here the higher frequency, here is the lower frequency. That means simple rule, when bk is minus 1, lower frequency, and when the bk is plus 1, higher frequency. So this rule should be followed or keep in mind for the better understanding. Okay. So thus MSK can be viewed either as an OQPSK signal with sinusoidal pulse weighting, or you can call it as also continuous phase frequency shift key, or CPFSK. You can see that phase is changed continuously, but according as the phase is changed, corresponding frequency is also changed. Okay, so we can see that MSK as frequency shift key with continuous phase. Okay, now coming to the MSK transmitter, it is very simple procedure. So for it can be simply generated or using the mathematical equation of MSK, which is nothing but uh, AQ AIT into cos pi t by 2t into cos 2 pi fct plus AQT into sin pi t by 2t into sin 2 pi fct. So this is the conventional formula. So by using this formula, we can easily generate it. So initially we are using a multiplier where there are two input, cos 2 pi fct and cos pi t by 2t. So by using this multiplier, there will be two frequency component, fc plus 1 by 40 and fc minus 1 by 40. That means higher frequency f plus and lower frequency m minus. So this signal is incident or applied into two different bandpass filter. First one is which have center frequency f plus, and second one has the center frequency m minus. So the corresponding output with the first bpf or upper bpf is 1 half into cos 2 pi fct plus pi by t into 2t, and the output of the second or lower bandpass filter is half into cos 2 pi fct minus pi by t into by 2t. Now we are using one adder and one subtractor. So the output of the first adder, that is xt. So xt is nothing but summation of s1t plus s2t, whereas output of subtractor, that is y1t, is nothing but s2t s2t minus s1t. Okay, so this one is the x1t and x2t, and if you use in the corresponding trigonometric identity, xt become cos pi t by 2t into cos 2 pi fct, and yt becomes sin pi t by 2t into sin 2 pi fc. Now if we multiply xt by ait, and if we multiply aqt by y2t, so we get ultimately If and then corresponding output are added by using an adder, and corresponding output will be nothing but MSK signal. Okay, so this is the simple block diagram for the MSK transmitter or MSK modulator. Now let's see the mathematical formula. So first, initial multiplier output is cos 2 pi fct into cos pi t. So it can be expressed like this: half into 2 cos 2 pi fct into cos pi t by 2t, and this is expressed like this using the trigonometry: cos 2 pi fct plus 1 by 4 tt, and 1 half cos 2 pi fc minus 1 by 4t. So first component, there are two cosine signal which have, first one is the frequency a plus, second have the second one has the frequency of a minus. So output of the first bpf is the half into cos 2 pi fc plus 1 by 4t, and output of the second bpf is the s2t, that is half into cos 2 pi fc minus 1 by 40 into t. Okay, now so now after addition and subtraction, so if we add them, you can see that half cos 2 pi fc plus 1 by 40 plus half 2 pi fc minus 1 by 40 cos a plus b plus cos a minus b. So output will be 2 cos into a into b, so cos 2 pi fct cos pi 2 by 2t. Similarly, this is cos a plus b minus cos a minus b, so that will be sin a into sin b. So this is sin 2 pi fct into sin pi v2. Okay, so we got xtt, xt and yt. Now if we just simply multiply with the ait and aqt with the xt and yt respectively, we get quadrature carrier: ait cos 2 pi fct in cos pi by 2 pi t by 2t, and aqt sin 2 pi fct into sin pi by 2t. If we just add them, it will give nothing but MSK signal. So ultimately we get ST, which is AIT into cos pi t by 2t into cos 2 pi fct plus AQT into sin pi t by 2t into sin 2 pi fct. Okay, now coming to the receiver side. So receiver is also very simple concept. It consists of two multiplier, two integrator, sampler and threshold device. The multiplier, okay, so initially in case of multiplier we need to regenerate xt and yt at the receiver section. That means this is the coherent type of detection, so we need to regenerate xt and yt, and after that if we multiply the MSK signal with xt and yt corresponding respectively, and the corresponding output is going to the similar way integrator and sampler and threshold device. Yeah, the output operation of this multiplier, integrator, sampler and the threshold device are the similar that is also already have been discussed in the QPSK or PSK. So we get ultimately AIT in the first threshold section and the AQT in the second slide, second section, and if we add them, we get corresponding final bit. Okay. So the demodulation work as follows: if st multiplied by xt, so cos 2 pi fct cos pi 2 by 2t, low frequency component of the result, the output of the integrator equal to AIT into 1 plus cos pi t by 4, and hence the polarity of the sampler output determine the value of AIT. Okay, and the operation of this quadrature channel is similar and determine the value of odd bits. So this one determine the even, this one determine the odd, and if we again multiply them, we get ultimately corresponding original baseband signal. Now we already mentioned that xt and yt can need to be regenerated at the receiver section. So this one is the corresponding synchronization circuit for to generate xt and yt and clock signal at the output end. So initially the incoming signal is st, that consists of two signal, high frequency and low frequency, a plus and a minus, and if we use the square law device, that means it will make the frequency of the corresponding signal will be doubled. That means we get 2a plus and 2a minus at the output of the square law device, And if we use two band pass filter whose center frequency is 2a plus and 2a minus respectively, we get the corresponding uh, 2a plus and 2a minus sinusoidal signal. Then we use the frequency divider that divide the corresponding frequency by half, and we get ultimately S1t at this end, and again we get S2t at the output end. Okay, and just if we add them and subtract them, we get ultimately get xt and yt. Okay, as we know that xt is nothing but cos pi t into to cos 2 pi fct. So if we add s1t and s2t, we get xt, and if we subtract s1t and s2t, we get the ultimately yt. And if we use s1 and st, okay, and multiply them and then use a low pass filter whose frequency up no cutoff frequency a plus minus a minus, then we will get ultimately clock signal of 1 by 2t. Okay, so by using this simple circuit we get xt, yt and clock signal, both of them. Now coming to the next part, bandwidth of the MSK. You can see that this plot shows the QPSK and MSK spectrum. Here you can see that the main, this one is the main side, main lobe, and this one are the side lobe. Here you can see that the side lobe for the MSK is very low, where the side lobe for the QPSK is very high. So this leads to the interference and other in-band radiation. Okay, okay. So by considering this fact, we can say that MSK is more efficient. Okay, spectrally more efficient. Next one is the bandwidth. If we consider null to null bandwidth, that means where the first null has been reached. So in case of MSK, the first null, the bandwidth, corresponding bandwidth will be 1.5 b, 1.5 f, and in case of QPS, sorry, yeah, in case of QPSK, it will be 1 f. Okay, null to null. But in case of, if we consider the practical case, that means we define the bandwidth as the spectrum where 95% of power is remain. So in, if we consider that kind of bandwidth, in that case MSK is more efficient compared to the QPSK. So we can say that if MSK is spectrally efficient modulation technique. Now coming to the signal space diagram of MSK. To draw the signal space diagram of MSK, we need to uh, express MSK like this way. So we already know ST MSK equation for the MSK has been expressed this type of equation, but here we use A as the amplitude of the corresponding signal, maximum amplitude. So A can be substituted by using root TPS. So we just substitute it by root 2PS. Now we use trigonometric identity, that means cos pi 2 plus 2 pi t cos A cos B and sin A sin B, that means cos A plus B plus cos A minus B, and next one is the cos A plus B minus cos A minus B. Now next, just if we rearrange them, we get this equation st equal to root 2 ps a1t plus aqt by 2 into cos 2 pi fc plus 1 by 40 into t plus root 2 ps ait minus aqt by 2 into cos 2 pi fc minus 1 by 40 into t. Okay, now we already know that if we want to draw the um, signal space diagram, we need to first express it in term of energy. As we know, ps into ts equal to energy, that is es. So we need to express in term of ts, bsts. That's why we divide, we use ts or introduce ts in both numerator and denominator. So st is written as like this: root 2 tsps a1t plus aqt by 2 into root over 2 by ts into cos 2 by fc plus 1 by 40 into t plus root tsps into ait minus aqt by 2 into root 2 by ts cos 2 by fc minus 1 by 14 to t. Okay. Now let us assume like this: AIT plus AQT by 2 is CHT, and AIT minus AQT by 2 equal to CLT, and uh, this part is phi HT and this part is the phi LT. If we use this, previous equation can be rewritten as like this: ST equal to root over TSPS into CHT into phi HT plus root over TSPS CLT into phi LT. So here phi H and phi LT can be considered as the orthonormal basis function that is required to draw the signal space diagram, and CH and CLT can take both 0 and plus minus 1, okay, depending on the value of AIT and AQT. Okay, so it can take this four combination 1 0 0 1 minus 1 0 and 0 minus 1. Okay, so uh, this is the signal space diagram for the MSK. So phi HT is drawn along x-axis, phi LT is drawn along y-axis, this part. So this one is the first symbol, second, third and fourth. So this one is the CH equal to 1 0, CL equal to 0, CH CL are 0 1, this one is the minus 1 0, CH is 0 and CLT is the minus 1. Okay. And the corresponding distance between them will be energy, that is root TS and PS. That means here you can see the amplitude TSPS. So obviously this one will be root TSPS. So the distance between them is the this one and this one. So distance, minimum distance is root over root TVPS whole square plus root TVPS whole square. That is nothing but root 2 TV to PS. So that is nothing but 2 ES. And if we express in term of energy EB, so this will be nothing but root over 4 EB. So the minimum distance is root 2 into TSPS. That means root 2 ES. Okay. So coming to the conclusion part. So in this class we have studied the MSK waveform mathematical expression. Now we have also observed the bandwidth and signal space diagram, where we can see that MSK is a very spectral efficient digital modulation technique, which have lower side lobe and that lead to the lower interference with the others communication channel. And moreover, MSK has another advantage, that means it has continuous phase, and it is also called as the shaped OQPSK, or continuous phase frequency shift key. These are the reference, and if you have any question, please post them.